way to learn is by doing. Don't you? Do you agree? Especially in this stuff, hands-on. I feel the experiential stuff of that. Oh, which, by the way, a little tangent. A group that came in from the Dublin Institute of Technology, I'm going back there and meeting up with some of those folks, and I'm giving a seminar to the larger group, to the school, on some research I've been doing. But I want you to think about this opportunity. I offer a study abroad class called Contemporary Issues in International Public Health. And what it is, it's a course that's at the sophomore level, but also at the senior/graduate level. So there's a sort of a 290 element to it, which is like the 201 class, and then there's like the 590 element to it, which is an independent study. So those of you who might be interested, I'm going to be coordinating a study abroad experience on spring break next year. It's going to be 1 week, and we're going to start out in Dublin. We're going to go counterclockwise around the country, which is really going to be a lot of fun. So, you know, we're going to head to the north, where the UK sort of takes over, if you will, go around to the other side, come all the way down to the Ring of Kerry, go up through Cork and so on, and then we're back. So we leave on a Friday, we get there on a Saturday, we hit the ground running. We're going to be on a bus, and it's going to be this movable feast all around the country of Ireland during spring break. So I know some of you say, well, it's just a great opportunity to go down to Florida and drink again with my friends or do whatever, or go to Ireland and drink. So they start at 18 there, so they're pretty accomplished by the time they show up here. Just anyways, they're looking forward to that. So if you're interested, shoot me a note, and I'll give you a little more information because it's just going to be fascinating seeing Ireland. You know, going up to Belfast and then coming around and going over and hitting some of these unique historical places around Ireland, and especially where some of my ancestors come from, which is down in Kenmare, which is by the Ring of Kerry in the south part, and I think one of the more beautiful places in Ireland. So it's like a big island, right? And we're just going to go all around it, hit it Saturday, and we're going to come back the following Sunday. Each day there's going to be something fun. So think about it, and because it's there, it'll be fairly affordable because we'll be moving around to the different colleges and so on. All right, back to this. So there were two NIOSH equations that came out. 1981 and 1991. And the 81 equation, when it came out, it had an action limit and it had a maximum permissible limit. And as we were talking about this, the thing that I found very interesting about the AL, and this is why it had to be revised, it had 4 criteria. 1, musculoskeletal injury incidence and severity rates were increased to conditions described in the action limit, which is called. And in that case, we were looking at 770 pounds. And remember that little stick figure that I showed you, that person lifting just with 50 pounds hanging out here? That, you know, we're looking at hundreds of pounds of force, over 600 pounds of force on the back, just in a simple diagram like that with an average person. Well, here we're looking at an action limit where you want to do something with 770 pounds of compressive force on the L5S1. And then it said basically looking at metabolic rates of 3.5 kilocalories, and then over 75% of the women and 99% of the men could lift loads in the action limit. And you remember, let's see, make sure I'm going the right way here. The maximum permissible limit, the MPL, this is what I was showing you last week, is that we were looking at 650 kg, or about 1,430 pounds, 1,430 pounds, and a metabolic weight of 5.0 kilocalories per minute, and 25% of the men and only 1% of the women could do this. So the AL, it turns out, when you look at this, is obviously it's a lot more reasonable in terms of more people being able to do it, but a lot of people were designing for the MPL, and said, well, we have sort of this green zone, a yellow zone, and a red zone. The red zone was the MPL, and a lot of people were confused by that, and they said, you really need to come out with something better than that. So they started working on it and said, okay, if you have your AL right here, and this is key, right here in kilograms, notice that they start out at 40 kgs or 90 pounds What's our limit for the 91? 51 pounds, right? So what happened in just 10 years? Did we get weaker? Was there a shift in the economic base, more women coming in, all this other? No. The answer is that when you look more closely at the H, right, which is that horizontal distance. Remember I told you early on that initially they were measuring students, and all of you, for example, if I were to take a cross-section of you, I can guarantee you your stomach distance to the spine is going to be a lot less than mine or most of the work population, which tends to be a little bit older. So they were using that information, and if you go up here, look at this, see, it was only 6 inches. That's it. If you change that number to 10, which is what it is in a 91 equation, this number comes way down very, very quickly and gets modified to a lifting limit, if you looked at the 91 equation, very close to 51 pounds. So, I could spend, a couple of hours on just this topic alone, but just know that if you run all these other numbers right here, some are modified, and I'll show you that, but the key factor right here, and obviously it's an easy question to come up that's a difference maker between the two, is that they simply changed from 6 inches to 10 inches, 10 inches from 81 to 91. That's it. And that's the horizontal multiplier. Ugh. Oh, I know what's going on. I'm just getting close to the other tabs there. Horizontal multiplier. So the H is the big deal. Okay? And here they had frequency. That came into play. We have a bigger table that you're going to see with the midterm. And this one just real simply, when you're standing, about table height, you can do many more lifts, right? As in 1 hour compared to 8 hours. Okay, just 3 different. But if you're stooping down less than 30 inches, like for example lifting from the ground, less frequency there, and even more so if you're doing 8 hours. So kind of simple, and you could sort of memorize that, and you don't have to, by the way. I'm just saying this kind of makes sense that you would do the least number of lifts if you're going from the floor in 8 hours compared to something that you're doing in 1 hour at table height, right? So one of the things that's really important here is don't always think in a biomechanical mode or in just calculations which generates forces. Think also in a physiologic mode where you're now looking at heart rate, right, and that energy expenditure. And this makes a lot of sense that you have to bring this down a little bit because you're expending a lot more energy lifting from the floor than you would be lifting from the table, and certainly less so under 1 hour versus 8 hours. That makes sense to everybody? So this idea of frequency really gets into the physiologic realm and not the biomechanical realm. So it's additive when this equation comes together. So then the maximum permissible limit, when you play it out, the AL is simply 3 times. Max is the maximum permissible one. 3 times that. So think about that and say, well, because one of the things is if you're going from one set of equations in 81, you're going to 91, you want to have some continuity. So I'll show you how that comes together a little bit later. So this is what the curves look like, and this is the distance between your spine and the front of your stomach, and look how quickly that thing drops down in terms of discount factor. If you go out, let's say, I don't know, let's go out, let's say 12 inches, something like that, coming across. Look at what you've done. You cut that, see that maximum value of 1? You're not going to exceed 1, right? In every some of these multipliers, even in the 81 equation, you're not going to exceed that. But if you just go out, to 12 inches, you've cut that thing in half. So whatever the recommendation is, you've got to cut it in half, right? So if the person's handling a 50-pound load, they've got to reduce it to 25 just because of the distance out on the H, right? And the others are similar to this, but see, there's much shallower here in terms of the distance. See the discount there? This vertical factor, the way this works like this is from the floor, right? Lifting from the floor. Now you're at table height. Now you're lifting from table height over and above. Where these things drop off are the limits, the reach limits for each one of these factors. Everyone got a sense of that? And these are just your different frequencies, right? The idea here, your continuous lifting lower, it's going to be less, right, 12. And if it's higher and it's over a shorter period of time, occasional, right, then that frequency is going to be different. So these lines and curves all make some sense to it once you look at it. And they are now carried over into the 91 equation, except we're going to have more things such as coupling and frequency. So this is what it looked like, sort of your acceptable lifting conditions right here. Then you had your administrative controls, and then you had your red zone, right? This is considered your red zone, this area right here. And the idea is that, of course, the further out you went, the more hazardous it became in terms of lifting conditions. So motivations then for changing, you need to implement non-sagittal repetitive lifts, non-mid-sagittal. I mean, we had to include twisting. That didn't exist in the 81 equation. Okay? Number two, they had to look at research findings relevant to the lifting equation in terms of any modification of what was already out there. What's new in the science? Do we need to change it? Next, they needed to look at a national strategy on ways in which they could knock down the problems with people getting back injuries as the equation could be used. And then something was a little more user-friendly. That's why, if any of you downloaded that document from the CDC website, only 51 pages, and I mean the font I think is like 14 or something, it's big, and explain to you what it is. And then the rest of the book is all about solving the formulas, right? It just gives you examples. So that was the objective there. So they wanted to look at the methods of continuity between 81 and 91. Methods can be expanded, non-sagittal, asymmetric lifting, and should the methods be calculated recommended with the weight limits, need to be revised based on new data. So they looked at all the literature, and they came up with key components. These are some of the people: Sue Rogers, Arun Garg, Mo Ayub, Arun Garg. Arun Garg's still out there. He's an interesting guy. But the others have kind of semi-retired. Yates, he passed away. But anyways, look at the four things right here. The physiological basis, biomechanical basis, psychophysical, and epidemiological. That is a question that I'm going to ask you, is that what's it based on? It's based on these four parameters. The physiologic basis, it makes sense, right, with the lifting and the frequency, as I mentioned. Biomechanical, that's very straightforward in terms of compressive forces. The psychophysical, this is what you determine as being safe. So if I give you a 25-pound load and I say, how do you feel about moving this, doing this job, 8 hours a day? You can say, well, first of all, the job sucks because I'm just doing this thing all day long. But can I handle the weight? Some of you say yes, some of you say no. So it's that kind of feedback that tells you, okay, how does that tie in with these other two? And then finally, based on the literature, where do we see the injuries occurring and what kind of information do we have about the weight of those materials being handled? Okay? So those four things. We had to develop a lifting location, a load constant. That load constant now in 81 was 90, and in the 91 it's 51, and develop appropriate multipliers. So here they are. This is it. This is what you're going to see on the midterm. You can see all these coupling multipliers. The coupling, frequency, asymmetry, distance, vertical, horizontal, and your load constant, that's always going to be, as I mentioned, you don't have to worry about that because it's a constant, and that is 51 pounds, about 23 kgs. Okay, that's always going to be there. And these multipliers then, as you can see the equation above, all go against that load constant right there. So intuitively you know that none of these factors really can exceed 1, right? You say, well, yeah, but they probably can because maybe this is less than 1, so that means that can be more than 1. No. What it means is that under an ideal lifting scenario, if all these equal 1 and just one of these is more than 1, that means you change the load constant to something more than 51 pounds. No can do. 51's 51, that's it. Not 51.2, 51.3, no. 51, that's it. So it always has to be 1 or less, right, for each one of these. This is what you're going to see in the exam in terms of the information that you need. So basically it'll be just this right here. And there's your load constant. These are the equations that you use, right? You don't have to memorize them. Don't worry about it. They're going to be supplied to you in the supplemental sheets. So this gets a little hairy in terms of the vertical. Then the distance. You'll have a table that I will give you for the frequency. That equation is straight up from the asymmetry, and then, of course, that's from the table. Now, please remember this. This is a good one. This is a difference maker. Okay, I'm lifting a load from here, and I'm putting it over here. How far did I turn? Ah! From a biomechanical point of view, how far did I turn?
0.
I'm shooting somebody. This is 0. 90. 0. 90. Right? It's about the twist. It's not about the overall movement. Right? It's about the twist. Come on now. It's about the twist. It's in there to trip you up if you're not listening. It's all about where I'm moving from the mid-sagittal plane. So look at this as I'm setting a compass. Okay? Boom, 0. 90. Back to 0. 90. Back to 0. Yes, I've moved from 0 to 180, but in terms of a biomechanical premise of this model, it's rotating from the center point, the mid-sagittal plane. Everyone got that? You're really going to thank yourselves if you listen to that and you get through that and say, I don't know what he's trying to do, and you'll just figure it out. Okay, so that is really important right here. That A, right? Make sure you get the A right. Okay. So we have this equation, and this is now, notice this, there's just one line, right? The recommended weight limit is just, this is good, that's bad. No middle zone. Okay? It's good, like green, yellow, red, no. Green, red. Right? So that's the new one. Just said, you go above the line, you got problems. Below the line, you're okay. This is not, this is not a law. This is not something that came down from the mountain. But for as a public health principle on those 4 parameters that I talked about, the physiologic, biomechanical, psychophysical, and epidemiological, based on those parameters, this works. Okay, so we have all these defined. I don't have time to go through these and read these to you because you've got the book, you can read it yourself, but understand the idea of a lifting task, a load weight, horizontal location, vertical travel distance, and asymmetry. This is really important. This V thing right here, listen closely, listen carefully. Ready for this? Your distance traveled is V1 minus V2. V1 is where you start the lift, and I don't care where the lift is. The lift can be up here, it can be on the floor, it can be on the table. That's V1. Wherever you're moving that to, let's say I'm moving it from the table to up here above my head, that V2, you subtract the 2, and that's your distance moved. Okay? So you're only going to have one D. Yeah, hang on. And the idea is that let's say you're below, 30 right here in this, and I'll show you this in a minute. Below 30, that number, that equation, will be such that it'll always be positive. Okay, so it'll never be negative, and I'll show you that. So neutral body position it gets into, lifting frequency, get into that, lifting duration, coupling, classification. This is important too. Understanding the difference between coupling of good, fair, and poor, and there's a difference between where you grab it, on the floor or at table height or 30 inches up. That's really important. And then last but not least is significant control. If I have a box of eggs and I lift it up, I have to, if I want to save those eggs, I have to gently set it down over here, which means I have to do the calculation for the lift at the origin, and I have to do the calculation for the destination. If I have a box of bolts, just metal bolts that I really don't care that much about, or a bag of sand that I don't have to worry about it splitting when I throw it, and I lift it up, or a bale of hay, and I lift it and I pitch it over here, I only have to worry about the origin of the lift. I don't have to worry about the destination because significant control was not required because precision in terms of releasing that load wasn't needed. So if you see an equation that you have to work out, think ahead, because so many students have done this, they get all stressed about time, they didn't thoroughly read the question properly, and they do both the origin and the destination when I said you're lifting a box of bolts and you're pitching it over here, and you say, I really don't need to do that second half of the equation. That's a big time saver. So if you think about it, that's important. I want you to understand the difference in recognizing risk from handling materials here, but not having to worry about it if you dispose of it this way. Or if it's fragile, you do have to dispose of it the right way, which is your destination. Okay, you saw this in terms of standing. And then this is your twist. Notice this is your mid-sagittal plane, right? So your angle, see this is always 0, right? So you might be moving from one end to the other, but 0 to the twist and back. This is the next concept you need called the lift index. And this lifting index is important because the load weight is what you have in your hands. And this is what you're going to calculate right here. The higher this ratio, let's say this weight is, I don't know, let's go 50 pounds again. And it says, okay, I'm lifting, this, let's say based on the lift that I'm doing, I'm twisting and so on, 15 pounds, right? You immediately see that it's going to be 3 times higher, right? 3 point something will be your product right here, lifting index, meaning that it's like an odds ratio. Anything above 1 indicates a greater risk for injury, for back injury, right? So if you have 1, you're great. In some cases you can go less, but the idea is that higher that number, the greater the risk is for back injury. Everyone with me on that? Okay, you will be given this. No. Will you be given this? No, you won't be given this because this is like a cheat sheet that you can do. That's in the book, and you won't get this because you won't have to do the calculation. But the idea is basically, if you're less than or equal to 10, your horizontal multiplier is 1, and see as you get out inches away from the body, look how quickly that horizontal multiplier drops. See, till you get to a certain distance out, 25, it's 0. You just can't apply it because you're out further than the average reach. And the same goes for vertical frequency, distance, asymmetry, and coupling. They all come into play. But you're going to have to do these calculations with the exam. Okay, so here's a simple job description. What I'm going to do is I'm going to leave this with you for your later readings, because I'm going to do one in class, and it's going to give us enough time to do one together, pair up, and then it's going to give us enough time to give us what you have and go home and do the third one. We okay with that? You have handouts up here, so did everyone get a handout yet? Who doesn't? If you don't have a handout, raise your hand. We're going to hand those out. Mike, I just have to turn the dot cam on, right? That's it? Okay. Here we go. Thanks, Mike. Well, I just got a lot worse, didn't it? What the hell? Oh, AF? Okay. Thank you. Appreciate that. Okay. Okay, so at the top, what you have is what you would see for the midterm in terms of the tables and so on. So you would get this information right here, and you get this frequency multiplier table, and you would get this coupling table. You'd be provided that, so you don't have to worry about it. But notice that it's giving you information up there at 1 hour, at 1 to 2 hours, and from 2 to 8 hours, right here. So that's your duration. This is your frequency of lift, right here. Then based upon this, then this gives you information that you need in terms of that frequency multiplier. Okay, so it's time-driven and it's task-driven in terms of frequency, right? How often you do it. And then notice this one here is a little bit tricky. It's a simpler table, but notice what's happening with this. There's a coupling multiplier, good, fair, and poor. And notice that what's happened is, okay, this makes sense. Okay, good at less than 30 inches gives you full 1. That's with handles. Okay, wrapping your fingers around something as in a right angle, 90 degrees, and holding on to like the bottom of a box, that would be considered fair. And poor is like a clamp. You just can't really wrap your hands around it in any way. You're just kind of clamping onto it. So this would involve cylinders. It would involve just things that you just can't get your hands under and around, okay, to close your fingers. But look at over here at basically 30 inches or desktop, right? It changes right here. It's 1 for good. It's also 1 for fair. So be careful, okay? And then it drops to 0.9 or a 10% discount if it's poor at 30 inches. So they don't want things that are poor out there in terms of handle. They really do like to see things with handles. So be careful with that. So the reason I need you to bring your calculators, this is not the only reason, but obviously, a good calculator will help you go through the math, a little bit easier this way with that equation. So the first one we're going to do is this right here. I think you have that, right? Does everyone have that? Okay. So it's basically starting out. This is a job. This is loading supply rolls, and this is out of the book. But notice I've changed some of the. Well, you probably don't notice, but for the sake of the argument, I've changed some of the parameters of this to make it a new experience for you. So with both hands in front of the body, the worker lies a core 25-pound roll of paper from a cart, then shifts the roll in the hands, hoists it by the sides and position of the machine, as shown in the figure, which I'll show you in a minute. Significant control of the roll is required at the destination. So you need to have now a calculation at the origin and the destination. You need to do both of them. And also the worker must crouch at the destination to lift the support of the roll in front of the body and so on, but does not have to twist. Good news. We don't have to worry about this part, right? So the task then, measuring the job, the vertical location of the hand, 30 inches at the origin and 10 inches at the destination. So here is where I begin, and here's where I end, right? So, okay, I'm picturing this now. It said the horizontal location of the hands, 15 inches at the origin and 20 inches at the destination. So basically, when I've got the load here, I'm like this, and at the destination, it's a little further out, down here, right? So now I'm putting that together. I said, okay, I've got it. So it helps to visualize it. Then it says the asymmetric angle is 0 degrees at both the origin and destination. No twisting. That's good news. And the frequency is 4 lifts per shift. Ooh, got to do some thinking about this. 4 lifts per shift, meaning certainly we're not dealing with something like 1 lift per minute or anything like that, right? So we have to think about that and say, well, do we have enough information to make some sense of this? I said, yeah, I think we do. So if you're looking at something like 4 lifts per shift, according to this, so they're going out there saying, well, okay, what's the 4 lifts per shift? We'll say, figure, okay, certainly under an hour. So we're at 30, right? So it would probably be something that basically one, here it is at 0.2, 1 lift every 5 minutes, so it certainly is going to be less than that. So this would be something that you would look at and say, okay, I got my frequency here. It could be 1. Everyone good with that? Okay, so here's our person. Here's our diagram. All right, and now what we're going to do is we're going to fill in some of this information. So the first one, I'm going to bring a pen. Did you bring a pen? I'll borrow it for a second. Great. Thanks, Mike. Okay, we said we started out at 30, right? So we're getting these from here, right? So it's 30 inches there, right? And then we placed over here. Notice that there's a center part right here that could be measured. And let's say in this instance, it's 15 inches right here. Don't just follow me, right? Okay, be patient with me. But really, look where the hands are. This is what we really are focusing on right here at the hands. And what I say, what was it at the destination? 10 inches, right? So that's the 10 inches right there. Don't look at the part. Look at where the hands are located, right? So we're looking at that 10 inches here, 30 inches here. We said we started out at what? In terms of the horizontal, we said we started out the horizontal location 15 inches, right? So we had 15 inches is where we started out from here. That's our H right there. And then where we finished, we said what? 20 inches, right? So we have 20 inches right here. I just kind of like to put these here so I can see what's going on. Say, okay, now I've been able to fill that in. So the ones I'm interested in are here, here, and here. So the important ones are 15 inches now is my horizontal at the beginning. I'm lifting at 30 inches from the ground. When I place the cylinder in its position, my H is now 20 inches, and my hands are 10 inches off the ground. My frequency, I've already determined, basically 4 lifts per shift, right? So basically going back and looking at that, it doesn't really get any less than 0.2, and 0.2 turns out to be 1.0 on my frequency right here. My asymmetry is there's no twisting. So if there's no twisting, then what you can determine is that would be 1. And the reason that works is because if you go to this equation right here and look at it, my asymmetry multiplier, you can see right there there's A. If that A is 0, then it's basically 1 minus 0, which is 1, right? Everyone good with that? Okay. So I think we have everything that we need. All right, so let's then see if we can pull this off. Okay, here's your worksheet, and this is the one that you're going to be using for B, so we'll just set you up here. All right, so we said the weight in this particular. Yeah.
Sorry, I missed at the bottom. You said no twisting.
Right.
Equated to something, so it meant something.
Yeah.
I didn't catch what it meant. Sorry.
It means you don't discount anything, right? So. See that A? If I had 90 degrees in there, then I would use that equation. I put 90 times 0.0032, right? That would give me a number, and then I would subtract it from 1. Okay? But I'm not twisting, am I?
Right.
So that A is 0. So basically, A times the 0.0032 is what? 0. And so 1 minus 0 is 1. Okay? We good?
Yeah.
Okay. So the weight of the object is 25 pounds, right? Now it has an L average and an L max. In this case, I'm not going to shift the weight on you because it'd be like a bin filling up with parts. You initially weigh it and it fills up some more, like maybe filling a container with fluid and then moving it over, and then it fills up to the top. It weighs more, something like that. Or maybe changing the contents so it's heavier. But in this case, it's just going to stay the same weight. So it's going to be 25 both times. Now we have my H at the origin is 15, right? And my V at the origin is 30. My H at the destination is 20, and my V at the destination is 10. Everything working out so far? So if I quick the math, remember I said V1 minus V2, what's my D? 20 inches, right? Because you're subtracting basically this from this. Everyone with me? Right? So, you know, basically think about it. 30 inches here, 10 inches here, I moved it 20 inches, right? So that's what happened there. And then asymmetry at the origin. Any twisting either time? Okay, that's 0. 0, right? Lifts per minute, we've already gone through that. We said less than 0.2, right? And our duration, basically, we're saying, you know, it's basically 4 times for a whole shift. So it's less than an hour, right? It's not going to take a whole hour to do this, right? So in this case here, less than 1 hour. How about my coupling? This is the important one there. Now this may be a judgment call, but remember what I said. Let's take a look at this. This is why it's important to read the book. Check out where her hands are. Are her hands in a 90-degree bend, or they sort of wrapped around this cylinder where it's like a clamp? How many agree with me? It's sort of like a clamp around there rather than a really good grip on something, right? Yeah, I would go with that. So we're going to say that at is poor. All right, so it's poor, and we're at 10 inches, so we definitely have discounted right down there, right? We know where that number is going to be. So now we just start going through the equation, start putting, basically using this information right here, okay, and I'm going to see if I can try to do this for you. Is that okay, like that? And I'll just slide that across. Be patient with me if you can't see it the whole time. So dividing then this number here, 10 over h, right? So we have 10 over h here, 10 over h here, right here. So we need to do that at the origin destination. So very quickly, what would be that number? Well, let's do the easier one. 10 over h on 20 on the destination is 10 divided by 20 is, there we go. This one's here, 0.667. Okay, verify that with me. Then the next one is 1. This of course, that's my load constant right here. And I did my horizontal, my vertical, my distance right here. So we're looking at, and this is at the origin. Make sure my math worked out here. I got 1.71. I'm just going to run through this really for the sake of time. 1, and 0.9. That's that poor, right? The 90%, 0.9. And that gives me 27.86 pounds. On the bottom, we've got 0.85. And you can do the math to confirm this with me. I've got 0.91, or is that 0.91? Yep. Sorry about that. This is a 0.91, not a 0.71. Apologies, because it is a short move. Same thing for here. Right, makes sense from that D. The next two are 1 again, full account, 0.9 again. And this one now is 17.75. So this is my recommended weight limit. Notice that the second one is a lot smaller than the first one. Why? Because the H is further out, right? Another 5 inches out, right? Yes? I mean, you want to see the answer? Okay. Okay. There you go. All right, so then what we do is we come down and we look at the weight that's being handled. So in this case here, it was 25 pounds, right, which is where this comes from. And then we're dividing in that 27.86. Look at that. It looks great because now we're less than 1. We got 0.897, I believe. I think that's what my number is. Going blind up here. So, and then the next one is down here, 25 divided by 17.75, which gives you 1.41. So, which is more hazardous, the origin of the lift or the destination of the lift? Destination of the lift, right? That's really important. So, what that means is that being above 1, the risk for back injury now is about 40% higher than if you had no risk at all things being equal. The first, though, the origin of the lift is actually less than 1, so it's not being protective, but you're not at risk for injury based on the origin of that lift, because you're lifting right at table height, there's no twisting going on, you got it next to your body, and you're kind of walking over here. Now things get a little dicey, right, because now you're trying to put it inside, the cylinder inside mounted on a rack, and that's how that all plays out. Okay, everybody, we good? Yes? What's the difference between poor and fair from coupling? Okay. The question is, what's the difference between poor and fair? The better question is, what's the difference between good, fair, and poor? Good is when you have handles. Okay, so this here, look at the edges. Okay, everyone concentrate on this because this is on the exam. So if you have handles, give me something with handles. Here's my cylinder, okay? Kind of should be a little bit bigger. Trying to find something that would have, where I could wrap my fingers around it. You've seen a standard like a banker's box, right? With have handles on the side, that kind of thing. That allows, basically to wrap your fingers around in a power grip, right? As opposed to this, it doesn't really allow me to get my fingers in there, but I can get them around and we're at 90 degrees, like this, okay? So this would be considered fair. But if I'm looking at if I'm doing a cylinder where I really can't wrap my fingers around it, just have to really, there's nothing really supporting this, I just have to kind of clamp it, hold on to it, right? That's poor, okay? Or like this. That's poor, right? If I wrap my fingers down inside and here, that would be fair. See how my fingers are? And then a good one would be if this had holes in it, I could put my fingers inside and I can grab onto it. A power grip. That's a good grip. Okay. Yes? Do the frequency one more time? Yeah. Okay, what's the key thing here in this job? How many times are they lifting per shift? 4 times per shift. Okay, they're doing 4 times per shift. Let's say I spread it out over the 8 hours, right? But it's done quickly, right? So it's basically done in such a way that I'm just able to do that. What's the cumulative amount of time that it takes to do these 4 lifts? I'm not saying, let's say I'm moving this can. Okay, I'm moving this can, and let's say I put it here. Okay, that's a frequency of a lift, and I put it there. Okay, now I'm not doing anything for another couple hours. You going to spread that out over 8 hours, or are you just going to look at the time it took me to do that lift? Just the time it took me to do that lift, right? So if it took, I'm saying 4 lifts per shift, that means that I'm not walking around for 3 hours, because you can see the diagram there, right? It's just the amount of time to lift that load and transfer it and put the cylinder in place. So it's less than 1 hour, okay? Because it's 4 lifts. It will specifically tell you, if I said, okay, this job is going to be, it happens, let's say, there's going to be, let's say, 10 repetitions per minute. I'll say that. And then I'll say that 10 repetitions per minute is going to be over a full shift, 1 hour or 1 to 2 hours. I'll say that, have to say that to you. But if I'm saying just 4 lifts over an entire shift, it's about the lift, right, rather than thinking about the shift. Because, I mean, it's not going to take you, there's nowhere in I say, person lifts this load and walks around for a couple of hours and then finally finds a place to put the cylinder and put it in. That'd be half crazy doing that. It's really about lifting from the rack and putting it in position. That's it. Yeah.
So was it 0.2 just because they did it so quickly that?
Yes. Yeah. 4 lifts, so it's over an entire time. It said, if you're doing 4 lifts, per minute, then we have a frequency. But say 4 lifts per shift, then we're just really talking about something that took a very minimal amount of time. Yeah. You have to be careful how you read that, right? So if I'm saying frequency over 8 hours, frequency 1 to 2 hours, frequency over 1 hour, then you can do that calculation. But if I'm saying, a couple of lifts over an entire shift, then really it's less than an hour to be able to accomplish those lifts. Okay? Any other questions?